Pleasure to introduce our second speaker of this session, Max Arnott, who was originally an undergraduate here in Lancaster and is now completing his second year, as he said, of his PhD under my supervision. So Max is going to tell us about the lattice of closed ideals of the algebra of bounded operators on a direct sum of classical Banach spaces and the incompressibility of its quotients. So please, Max.
Thank you for the introduction. Yeah, thank you for having me on to speak. Thanks, Benza, for a great talk as well. So it's, it might be the title for the longest title in the conference, so that's an honor as well. So I'll start off with a few definitions. So a closed ideal is a subspace closed in the norm topology. So it's closed under addition and by multiplication by arbitrary elements of the Banach algebra that it's a subspace of. We're going to use B of xy for the space of bounded operators, and we're going to use B of x for B of xx. An operator ideal is an assignment sending each pair of Banach spaces to a subspace of their space of bounded operators. So for every pair xy of Banach spaces, there has to be exist a non-trivial one for that assignment, and for any quadruple w x y z of Banach spaces, any s from w to x, t from x to y, u from y to z, UTS has to be in I of wz. And we'll use I of x for I of xx, which is quite natural. So examples of operator ideals which we are going to be using. So G of D is going to be the operator ideal of operators factoring through D, and we're going to use the norm closure of that. So all of the operators ideals that we're going to use today are closed operator ideals. It's actually an operator ideal if and only if D is isomorphic to its square, but everything we use today will be isomorphic to its square, so we don't need to concern ourselves with that. So we're going to use the kappa compact operators as well. So it's a generalization of the compact operators. I think Matt Dawes came up with these ones in the first place. And the Banach spaces of interest to us are C0 of gamma for gamma sum cardinal, and LP of gamma for gamma sum cardinal as well. We're also going to need the finite dimensional versions of the LP space. So it's just n tuples with the P norm. We're going to use the C0 sum of the finite dimensional L2 spaces as well. So that is the norm. So the elements of that are sequences of elements of Hilbert spaces. And for the norm, you take the supremum of the norms of those elements. An operator T factors through an operator S if S is a factor of T. And an operator T factors through a Banach space Y if we can express it as a product of two operators, one going into Y and the other one coming out of Y. So now we sort of give the outline and motivation of the talk. So it's all about classifying the lattice of closed ideals of a space of bounded operators. So Matt Dawes found the lattice of closed ideals on B of C0 gamma and B of LP gamma. So that's for P between 1 and infinity, but not including infinity, and gamma infinite. Larson, Loy, and Reed found the lattice of closed ideals of B of the C0 sum of the L2 spaces. And Larson, Schlumprecht, and Schack then found the lattice of closed ideals on the bounded operators of the dual of this space. So I will say now that within this talk, we're going to be working with the direct sum of C0 gamma and this C0 sum here. The results also hold for the duals. So L1 of gamma plus this L1 sum here. But there are just a couple of things you have to do ever so slightly differently. So I've done it in terms of this C0 sum. But all of the results hold for this this talk if you replace all instances of C0 with L1. So for classical Banach spaces, that's everything we've got. There are some more exotic examples where we know all of the closed ideals. For example, if you went to Niels's talk on Monday at Garth's retirement session, he explained about a C of K space which has few operators, in the sense that its operators are sums of multiples of the identity and separable range operators. And the space of bounded operators on that C of K space has exactly 4 closed ideals. So what we're going to do is take the direct sum of the C0 gamma and this C0 sum of Hilbert spaces, and we're going to find a lattice of closed ideals of that. We'll then show that if we quotient this Banach algebra by any of its closed ideals, we get a uniformly incompressible, the uniform incompressible property, which I will define when we come to that. So what we need to do is sort of talk about operators on a direct sum of Banach spaces in terms of matrices. So we can identify any operator by a matrix Tij, and the ijth entry goes from xj to xi. So addition is just entry-wise. Composition of operators is simply matrix multiplication. So there's nothing interesting going on there. I'm sure everyone's seen it before. The action on a pair x1 plus x1, x2 in this direct sum is just given as follows. You can also recover any quadrant of the matrix just by using the inclusions and projections. So if we let Jj be an inclusion from xj to x1 plus x2, and qi being the quotient from x1 plus x2 to xi, then we can say that Tij, the ijth quadrant, is equal to qit jj. And then closed ideals are subspaces of the space of bounded operators. So each quadrant has to be a subspace of the bounded operators on that particular quadrant. Now, something that's quite easy to prove is that in any closed ideal on a direct sum, on the bounded operators of a direct sum of Banach spaces, the first and fourth quadrants have to be closed ideals of their respective space of Banach spaces. So given that the spaces we're working with, we know their full lattices of closed ideals, we know what the possibilities for I11 and I22 can be. And for that reason, we're mainly focusing on what can be in the off-diagonal quadrants. So here are these lattices of closed ideals I was talking about. So for the L2 sum, the C0 sum of the finite dimensional L2 spaces, you have 4 closed ideals. So you've got the trivial ones being 0 and the entire space of bounded operators. And then you've got the compact operators and the operators approximately factoring through D, where D is C0 in our case, but as I said, it also works for L1. And the lattice of closed ideals for C0 of gamma, or LP of gamma, is given by 0, the compact operators, the LF1 compact operators, all the way going up to the gamma plus compact operators, which are equal to the entire space of bounded operators. So the definition of these, an operator is kappa compact if for every epsilon greater than 0, the closed unit ball of the domain of the operator contains a subset x epsilon with cardinality strictly less than kappa, such that the infimum of the norm of t x minus y for y in this subset of the unit ball is less than or equal to epsilon for every x in the unit ball. So what you'll notice is, because this is strictly less than, if I set kappa to be gamma plus, where gamma is the cardinality here, what you'll end up with is you can take x epsilon to be the entire unit ball. So that's why the gamma plus compact operators are equal to the entire space. It's true for any time you've got a space of density gamma, kappa, gamma plus, k gamma plus of x is going to be the entire space of bounded operators. So a closed ideal on this direct sum, on the bounded operators of the direct sum. So we're going to write E for this C0 sum of the Hilbert spaces now. We know that the possibilities for the first and fourth quadrants are going to be given by 0, compact, approximate factoring through C0 operators and the bounded operators in the first quadrant. And the fourth quadrant is going to either be 0 or some kappa compact operators in that position. So what we can do is you can quite simply prove that if I is an ideal of the bounded operators on a direct sum of Banach spaces, if any of its quadrants are the compact operators, then all of them must be. And that goes in converse as well. So the only time the compact operators can appear as one of the quadrants is if all of them are. And the same goes for 0. So what you can do using this is just rule out the first two ideals from these quadrants as well. The direct sum has the approximation property, meaning that the compact operators are the closure of the finite rank operators, which tells you that the smallest non-zero ideal is the compact operators here. And then what you do when you combine these results is you can say if a closed ideal on this Banach space of bounded operators strictly contains the compact operators, then it must be of this form. So it must have first quadrant either approximately factoring through C0 or the entire space of bounded operators. And the fourth quadrant has to be kappa compact, where kappa is at least F1. So the identity operator on C0 factors through non-compact operators on the operators going from C0 gamma to E and from E to C0 gamma, all of which factor through C0 themselves. So I haven't proved that here. You do have to do a little work to prove it, but it's not nothing crazy. This implies that all of the operators are the operators factoring through C0. And it follows that for any closed ideal of this space of bounded operators strictly containing the compact operators, the quadrants 2, 1 and 1, 2 have to be the entire space of bounded operators. So from factorizations given by Dawes and in Larson, Loy and Reed's paper, we know that the identity on C0 factors through every non-compact operator on C0 gamma and E respectively. When we combine the results from these bullet points, what we get is that if a closed ideal strictly is not, sorry, a closed ideal of the space of bounded operators on E plus C0 gamma is either contained within the compact operators or contains the operators factoring through C0. And this gives us our first three inclusions in the lattice of closed ideals. So yeah, here we've got the lattice of closed ideals. We know that the rest of them, their off-diagonal quadrants are the entire space of bounded operators on their respective Banach spaces, and the other quadrants are of the following forms, so here and here. So the cases for when I11 is the entire space of bounded operators, well, all of them operators are going to be kappa compacts when kappa is bigger than or equal to F1, because the space E is a separable space. And what this tells us is that the ideals that are in this form are the kappa compact operators themselves. So now we're able to paint this picture for what the lattice of closed ideals looks like. So the ideals J, these are of the form where the top quadrant is the approximately factoring through C0 operators, and the fourth one is the kappa compacts, and these ones are the kappa compact operators. There is a bit more work that needs to be done to show that everything just falls into place nicely, but we're going to gloss over that because we want to get on to the next topic, which is incompressibility. So Banach algebras are incompressible if every continuous injective Banach algebra homomorphism from them into another Banach algebra have to be bounded below. So this was talked about in Matt Dawes's talk on Monday. It also was talked about by Bill Johnson in the Banach Space webinar back in January, I think, and that's available on YouTube. I would recommend that talk. So it's uniformly incompressible if the Banach algebra homomorphisms into another Banach algebra, the lower bound of them depends only on the norm of the homomorphisms themselves. So here's a proposition from that Bill Johnson talk. A Banach algebra is incompressible if and only if the norm is unique, in the sense that every continuous algebra norm is equivalent. And this sort of gives another place where this was studied before, the PhD thesis of Griff Ware. So this is all about uniqueness of norm properties of Calkin algebras. It explores this line of research, and that's what gives a lot of incompressibility results. So it gives ones that are useful for us. He proved the quotients of B of C naught of gamma and LP of gamma by any of their closed ideals. So these are called the kappa Calkin algebras because they're the quotients of the bounded operators by the kappa compact operators. So these all have unique algebra norms. And he also showed this for the Calkin algebra of the C naught sum we've been using. So from the methods that he gives in his paper, so he uses block basic sequences to prove these kind of results, and you can combine the results and prove that the Calkin algebra of this direct sum plus our C naught of gamma space, that Calkin algebra is incompressible. So yeah, this is sort of how we prove incompressibility results from here on. And this is, I'm not going to prove it here because it was in Bill Johnson's talk again, which I'm going to keep referring to. So if there exists a non-zero element A in a Banach algebra, capital A, and some finite m less than infinity, such that for every norm 1 x in A, there are B, C, and A with the norm of B times the norm of C less than or equal to m, and A equals BXC, then A is incompressible. So when we can select A to be an idempotent, A is uniformly incompressible. So this is a very useful theorem to have because these kind of factorizations exist. So an element of Banach algebras factoring through all of the unit elements of the Banach algebra is really useful results when classifying closed ideals. An example of it is when we take X to be our direct sum, our C naught sum of the finite dimensional Hilbert spaces, every operator which doesn't approximately factor through C naught, which is norm 1, the identity on this space factors through it. And this was used to classify the closed ideals of this, the bounded operators on B of X. So what we have to do to prove incompressibility then is find the upper bound on the norm of U times the norm of V. I will add that this proposition here gives an easy way of showing that the entire space of bounded operators itself has to be incompressible, in fact, uniformly incompressible, or any subalgebra of it which contains the finite rank operators. And that's because you can just get everything to factor through a norm 1, rank 1 operator. And it's quite trivial to do that in a bounded way like this. So for our example here, we can actually always choose U and V for which the norm of U times the norm of V is less than or equal to 2. I'm going to do that right now. So what we do is we take T to be an operator which is bounded on X, and for any operator of this form, we can write T as a matrix Tij, and the ijth entry goes from L2J to L2I. So importantly, we can perturb T by an arbitrarily small compact operator, and then we can consider it with a matrix of finitely supported rows and columns. So we define this M epsilon quantity. So if S is from a finite direct sum of Hilbert spaces to X, finite sum of L2 spaces, we set M epsilon of S to be the supremum number M for which S of the projection of L2 to the 1 over G1 perpendicular plus ... plus P, the projection from L2N to the orthogonal complement of Gn. So if S composed with this direct sum of operators has norm greater than epsilon for any subspaces, Gj of, Hj here should be L2 to the J, of dimension at most M. So the idea of this is M is the largest natural number for which if we remove a space of dimension at most M from each of the Hilbert spaces in the domain of S, then we still have an operator which is larger than epsilon in size. I find this definition a bit easier in words than it is when you write it down like that. So because we have that T is, we can consider T as a matrix of finitely supported rows and columns. When we take Qn, the projection onto the nth Hilbert space, Qn of T, we can consider M epsilon on that. So we do that just by ignoring the Hilbert spaces in the domain of T on which it acts trivially here. On which Qn of T acts trivially, I should say. So Larson, Loy, and Reed's paper gives the factorization, the identity factors through T. And from that paper, from their proof, what you can do is prove that R can have norm at most 1, and S you can take to have norm less than or equal to 1 over epsilon. Epsilon you can take to be any value for which the supremum of M epsilon Qnt for n natural is equal to infinity. What we showed more recently is that you can actually take epsilon to be anything less than the quotient norm of T. And what that tells you is that when you take epsilon less than the quotient norm of T, you get that M epsilon Qnt is equal to infinity. That's true whenever T does not factor approximately through C0. And this basically ties the result together. So if you take any T in the quotient space, B of X over the operators factoring approximately through C0, you have this, this factorization through the identity, and you also know that it's bounded. You just take half epsilon to be halfway here. So we've already seen that every closed ideal of this bounded, this space of bounded operators on a direct sum, strictly containing the compact operators, has that its 1, 2, and 2, 1 quadrants are trivial. They're the entire space of bounded operators. And I've just noticed here that these should say C0 gamma instead of C0. So apologies for that. So quotienting this space of bounded operators by such an ideal, you're going to get elements of this form. So in the 2, 1 and 1, 2 quadrants, you're going to be adding the entire space of bounded operators. And what that means is you can identify anything which only differs in these 2 quadrants. So they get quotiented away, basically. And lastly, I didn't prove this because there isn't going to be time, but the uniform incompressibility of the quotient spaces in such a case, it follows directly from the uniform incompressibility of the quotient of the bounded operators on C0 of gamma by its first quadrant and the direct sum here by its fourth quadrant. So the important thing here is that once you know that in these quotient spaces, the off-diagonal quadrants are going to get quotiented away, you end up with the incompressibility following from the uniform incompressibility of the quotient space in the other two quadrants. So all of the ones where I is bigger than the compact operators are of this form. We know from Griff-Ware's results that the Calkin algebra of this direct sum is going to be uniformly incompressible, and the other cases are it's just the I equal to 0, and in that case you've got an entire space of bounded operators, so it's trivial. So thank you all for listening, and I'll take any questions.
Thank you very much, Max, for a very nice talk. Are there any questions, please?
Can I have one question, please?
Sure.
Have you thought about L infinity in terms of incompressibility?
I don't think we have. We've been looking at a couple of other spaces. So there's some different LP sums of different finite dimensional LP spaces that we've been looking at, because although they don't have their lattices of bounded operators fully charted out, you do have some of these factorization results. So I've been looking into a couple of those, which they proved quite difficult. And also we've been looking at the C of K space that Niels talked about on Monday with few operators. And that one, it seems like it's gonna be incompressible, but the quotients of it by any of its closed ideals will be, but we haven't got there yet. So anything could happen. But no, we haven't looked at L infinity, unfortunately.
Thank you.
We should probably add, I mean, there is this draft paper, the one that Bill Johnson spoke about in the Banach Spaces webinar back in January, and where this incompressibility property was referred to as IHAB, I think. But I understand they changed the terminology subsequently. So this is a preprint by Bill and Gideon and Chris Phillips. So I think they are looking at capital LP in particular. And I think, is that right, for the reflexive range?
Right. Yes, that's correct. That was the main thing.
So that, yes, so that was one of the cases that was left open, I think, by Griff-Ware. But I don't know, Bill, did you look at L infinity?
No, we didn't.
Okay.
Actually, I haven't really thought about it all.
Okay, are there any other questions? If not, I suggest we thank Max again. And then we'll have a